Imagine you are sitting in your office high above the city, and suddenly the ground begins to tremble, the walls begin to vibrate, and you can feel the building sway. You begin to panic. In just seconds, your world could change forever. You start having the fearful thought: will your structure collapse or not? Will you make it out safely? In a world where over a billion people live in earthquake-prone areas, understanding which building can survive earthquake ground shaking motion is not just an academic question. This question is a matter of life and death. But have you ever wondered which type of building is most likely to survive an earthquake? Is it low-rise buildings or high-rise buildings? Some experts argue that it is safer to be inside a low-rise building during earthquake ground shaking motion, while others believe that due to the advancement in engineering, it is safer to be inside a high-rise building during earthquake ground shaking motion. So, which type of building really stand the test when the earth starts to rumble? First, let's understand what happens during an earthquake. When tectonic plates shift, they release energy that creates seismic waves. These waves can cause the ground to shake violently, impacting buildings differently based on their height, based on their designs, and also based on their materials. The severity of this shake can vary greatly, which is why building design is crucial in earthquake-prone areas. The probability of failure of a structure will depend on how it was designed. It is not as easy as it sounds. Designing a structure to withstand earthquake, be it high-rise or low-rise, comes under a lot of assumptions, right from the analysis approach, the assumptions in building code, and the probability of the earthquake. Let's see why a building may collapse. A building may collapse if the ground motion or ground acceleration, or we can say if the intensity of the earthquake is higher than what is calculated. When a design level earthquake, which has the probability of incidence of 2% in 50 years, is less when compared to the actual earthquake ground shaking motion felt by the building, then there are chances that the building might collapse. If the building is designed without any sort of ductile detailing or reinforcement as per the building code of that particular region, then that building has a higher probability of collapsing than other structures. A building may collapse under an earthquake if there are a lot of irregularities during the design and construction phase. If there are a couple of very short columns, during an earthquake, these short columns will take more load and collapse because of the high shear demand and low displacement capacity. Due to these irregularities in the structure, the load part will be very complicated, which may lead to failure. The presence of weak story in a building may also lead to failure of the structure during earthquake ground shaking motion. A weak story is a story that has its stiffness less when compared to the stiffness of the adjacent stories. This weak story will drift more than other stories, resulting to failure. Now we understand why a building may fail or collapse under earthquake. Let's go back to low and high-rise buildings. A short building has a simplified behavior. The primary mode of short building has around 60 to 70% of the primary mode participating factor. This will mean that the building will behave as a vertical cantilever. If you follow the code right and calculating all forces correctly with a good ductility factor, you will get a good design of the structure. And for top buildings, they have a significant higher mode effect. Higher mode in a structure will lead to high shear deformation. This shear deformation will demand more shear strength and ductility. If you follow the traditional response spectrum analysis for a tall building, then you will not capture the right ductility demand and the building has a higher potential to collapse. In order to understand higher mode effect, we will see an experiment. For short buildings, take a plastic scale and shake it continuously. It will vibrate just like a diving board attached to the side of a pool. Now, if you take a whip and whip it, you will notice it no longer oscillates like the plastic scale. So, with this approach, a taller building will be more susceptible to collapse than shorter buildings. If we perform performance-based design where we create a computer model and test the building under various rigorous earthquake shaking, thereby having a more accurate result, the high-rise structure will have more chance of survival than a low-rise structure. Because short buildings act more like a diving board, we can do a test called pushover analysis where we test the building maximum capacity deformation. Increasing the strength of a structure will reduce the ductility of the structure. Earthquake demand more ductility, and you need to understand that earthquake loves structures with low ductility. So if you think by increasing the strength of a structure, this will make the structure safe from earthquake, you will be wrong, because increasing strength demand for even more ductility demand. This will make your building more susceptible to earthquake failure. So regardless of it being a high-rise or low-rise building, when you increase the strength demand, this demand for even more ductility, which in return make the structure susceptible to collapse under earthquake ground shaking motion. The survival of a building during an earthquake will depend on the strength of the ground shaking produced by the earthquake. Low-rise buildings are more affected by short and frequent high-frequency wave produced by the side-to-side earthquake motion. Let me explain. Take for instance a small boat sailing in an ocean. Several small waves in quick succession can cause the boat to capsize. This also applies to low-rise buildings. They have a high chance of collapsing in the event of a high-frequency earthquake. Now let's say we take an ocean liner, for example, instead of the small boat. These several waves which cause the small boat to capsize may not necessarily affect the ocean liner, but if there is a large swell, this will greatly affect the ship and may cause the ship to capsize. This same logic we apply to a high-rise building. Sustained slow shaking will cause severe damages to a high-rise building. So, in conclusion, both types of structure must be regularly inspected and maintained in order for them to remain structurally sound and capable of weathering an earthquake should one occur in your area. No matter what type of building you own or manage, taking steps to ensure its safety may mean the difference between life and death later on down the road if disasters strike unexpectedly.